Yes, you got it. We all remember how you volunteered.
Where's the thing so I can hide what I'm doing with my finger? All right, fine. I'll go look for the minutes template. It's around here somewhere.
You can just take the last times and just, change the dates and the names and stuff.
Yeah, that's what I'm going to do.
That's why I made it such a blank form where you just fill in the empty blanks.
Yeah, it makes it easy enough. I really have no excuse. So I just have to find it. It's around here somewhere.
Okay.
Right. Recent documents. Lowbrow minutes. All right.
I got to start.
Adrian's a trooper, I'll tell you what. Sees a forecast, it's going to be clear for a minute out on the shore of Lake Michigan and just drives out there.
Yeah.
That one picture particularly, though, was pretty cool. You could see the moon, you could definitely see Jupiter and Saturn. That was nice.
Yeah, that was one of the last ones I took, and I tried to take it kind of low to the water. Yeah, it was clear for a while. It was clear enough for me to see what I was looking for, and it worked out. I think. Yeah, there's a couple of different shots that I took that I didn't share, but where's all that Grand Haven crap?
Okay.
Yeah, there are a couple that I have to figure out what I want to do with them. Let's see if I can. Yeah, I can share screen because why not? So there's the moon over here. This is a wall of cloud that prevented me from catching a sunset. I was actually there in time for a sunset, but wall of cloud prevented that.
That's what Ypsilanti was doing this afternoon. It's like I had a clear spot overhead. I could see the moon, a little bit foggy here and there, and a wall of clouds directly over the sunset. So I couldn't even see the sun. Like, what the heck?
Yeah, it was like that on the lake, and I took this shot because it included both of the lighthouses, and that turned into what probably amounts to street photography more than anything. I usually don't shoot with a bunch of people.
Hey, Adrian, is that ice on our right-hand side of the pier?
Yes, it is. Let me go back to that shot.
This early.
I got ice on Ford Lake right now.
Yeah,
it's a scare.
I got ice on my driveway.
Yeah, there's ice. Let me go close in to if this will work. Yeah, there these patches. There's my backpack, and there's a patch over here that I didn't show. Nothing but ice. If you walked along there, you basically risked falling into the lake. It was that slick.
Yeah, that could ruin your whole day.
Yeah. So I think this is one of the ones that I did show. The conjunction wasn't quite visible to the sensor yet. It's like it's barely over here. People were seeing it and I wasn't, but I was like, it's okay. Camera will catch it. And then there's the series of shots where I did have it. I liked this one. I wish I could do something more with it, but there's a conjunction right there. And you can barely see it. And that's the part of the lighthouse, the pier that's all ice. I actually shot from over here. You got to be careful because whoops, you fall into the lake and that's pretty deep. Yeah, and it's cold. So kind of another street shot, but yeah, so I had someone over here. I took a long exposure back to Grand Haven. It's a beautiful little town. I haven't straightened the horizon on that one yet.
I actually have a phone customer in Grand Haven, North Shore Marina. Yeah,
that is it's a cool place somewhere around here. This photo, which I'm going to do something with at some point.
Oh, that's nice.
Looking up
at
the lighthouse. and opened up some stars. I'll probably do something with that. So, and then here go all those. So Chris Sarnecki suggested that I do this with this photo, and
That's beautiful.
Third line, yeah, that was.
Well,
So yeah, I shot this. That's the lake. That's the shelf that never went away, and the moon covered there.
But
That's what I liked about.
But seeing the shine on the lake from Jupiter and Saturn is pretty cool.
Yeah.
Yeah. No, I agree. There's even another star over here, and Vega was over there somewhere. I cropped it out.
If
I like this one too.
If you brought that other one with the you had with the close up of the two planets, and crop out the moon, you could say out of the view from Tatooine.
That's not a bad idea. I may do that. Yeah, the water was almost like this in real life. I mean, it's smoothed out because of the long exposure, but it really was, I know we're close to start time, it really was about that smooth, just, in real time. And from what I've heard about the lake at this area, it's usually a lot rougher this time of year. And I'd love to do something with this one, but
I don't see Ryan.
Sorry, Adrian, where is this?
This is Grand Haven. Let's see if there are some more shots that I actually took when I turned around and took pictures of Grand Haven itself. They haven't shown up here, so I'm going to be lens flare. There's looking from the pier to the beach, and there's the town of Grand Haven right there. 2.5 hours from where I'm at. It wasn't too bad a drive, and I'm not sure where I'm pulling this light in. Oh, from just walking off the pier, you got all that light, so it illuminated the beach, but then you got the water. That's Grand Haven's a beautiful place. A lot of people were there, and even as I'm taking these photos, it wasn't long before you'd see another group of people show up, walking along one side or the other of this pier. This is the place for people to go to hang out. That's about how dark it really got. That's where people hang out and spend time. I don't know where I'm getting on the green in the water. I had to do something about that, but that was a fun little trip. Say it again, Doug.
Is that bioluminescence in the water, or just the way the film the sensors caught it?
I think it's the way the sensor caught it. Yeah, not 100% sure actually. These last couple shots just singled out earlier in the day. That's one's pretty nice. There you go. That's all the people that were over there. Used the zoom lens to pick that up. I was basically here, and I zoomed in all the way. And now I've seen pictures of this lighthouse, and a lot of you may have too. You've got the people here. Well, I've seen pictures where there were waves here crashing up against this thing and, enveloping the back of this lighthouse, and more big waves over here. So this was an unusually calm night. And I was told by a lot of the locals that, normally you can't walk on the pier because the waves are too high. So Ryan. I'll have to try and go back. Say it again.
I just noticed Ryan is now online.
Okay.
Cool.
So I'll stop my presentation.
You're fine.
I've never seen a lighthouse that short.
Yeah, well, they have two of them, so they make up for it, I guess.
It sticks out quite a ways too, so
yeah,
that's a good walk out to that lighthouse in the middle of the lake.
Yeah, for those that are there. Failed attempt at trying to get Orion at Lake Hudson. But the Horsehead came out halfway decent. So it's getting there. Well, no, actually,
How
that's a
long?
bit of a mess. That's a 90-second exposure, I think. Or no, 105-second exposure. I was looking for something else, but I'll find it later. Go ahead and stop. And prepare for these minutes since I've been told I'll be taking them. So I'll be splitting my screen up here. There the Zoom meeting goes here.
See, you joined
Goes
just
there.
about 30 seconds too late to save yourself, Adrian.
I don't think it was gonna matter. I had discussed doing the minutes
Yeah, you had said something about it. so you were nailed
prior
right.
to even joining. So
Yeah.
I think I was doomed from the start. That's okay. It's the way it is.
And in case you didn't
That's okay.
know, we appreciate really what Ryan had to go through to join us. He actually flew out to California. What was it, this afternoon? In fact, you just got there not long ago, I believe.
Yeah, just last night. I had
I was thinking it was today.
no, thankfully not that
Oh.
crazy of a trip, but I didn't
Okay.
get in until around midnight, so it was really beautiful. I'm about an hour north of San Francisco, so the
Okay.
stars are really showing up nice and clear here. It always kind of stuns me when I come home, just how much darker the sky is compared to Ann Arbor. Like, I'm sure if you go an hour away from Ann Arbor, it'd be even better than here, but it's pretty nice.
2.5 to be exact. You go to the thumb from Ann Arbor, and it darkens considerably. I had a chance to be out in San Francisco, so the little
Really?
slideshow I was doing, I got a slideshow for that too. I got bridge shots. So
That's awesome.
yeah, we'll. I know we're running on time, so I think most here are probably going to be more interested in what you'll have to tell us than the bridge shots. But we'll have to show those later after the fact.
Okay, so should I start sharing my screen then?
No, I'm going to go ahead and introduce you first. I
Okay.
usually wait until about 7:35 just to let the people who are
Okay.
going to be a little bit late come in. And I'm showing 7:34 right now, so I'll tell you what, that is close enough. So, welcome everybody to the December edition of the University Lowbrow Astronomers. I'm Charlie Nielsen, the president of the club, as you probably most people know. We have several officers here attending. We'll get some reports from them later. But as is always the case, we have our guest speaker as the first part of our agenda. That way, if anybody really just wanted to join for that and then had the audacity to not join our business meeting, oh, it's quite all right, then, they can leave after Ryan's talk. So with that, let me just switch something here. As I mentioned, our guest speaker tonight is Ryan Farber. Oh, and before I mention, as always, I need to inform everybody that we are being broadcast also on YouTube and recorded. So with that, Ryan is a graduate student working in the University of Michigan Astronomy Department. He attended Wheaton College from 2011 to 2015, where he earned his Bachelor of Arts in Physics. He then came to our favorite university, where he is on track to earn his PhD this coming August. Ryan Farber has been awarded by Wheaton College, Pavley Institute for Theoretical Physics, and the U of M several times. Ryan grew up north of San Francisco, where he happens to be now, by the way, before moving to Boston to attend Wheaton College, where he was an observatory assistant and a member of the Amateur Telescope Makers of Boston Astronomy Club. He also co-founded the Physics Club at Wheaton. He and some fellow graduate students are building a 6-inch Dob, but currently the primary is locked up at Randall Lab. Wow, he sounds like a perfect member for our club, especially if he ends up using some duct tape on that telescope. But as it turns out, Ryan actually is a member of our club. He also is a prominent member of Michigan Dark Skies, as well as many of our other club members. As you know, that's the people doing the trying to get a light ordinance in place in Ann Arbor, and hopefully we'll expand that further later. Currently, Ryan investigates computational solutions to observational puzzles of galaxy formation and evolution. Typically, discrepancies between theory and observations arise due to the neglected. Oh, sorry, I just saw a message come up. Due to neglect of key physics. He performed the first study of cosmic ray acceleration of galactic winds that included the temperature dependence of cosmic ray transport. Tonight, Ryan is with us to talk about what would seem to be the end of galaxy evolution in a presentation titled, Will the Milky Way End in a Whimper or in a Bang? Forecasting Galaxy Evolution at Billions of Years. So with that, let us welcome Ryan Farber. Take it away, Ryan.
All right, thank you. Thank you all for having me tonight. Hope that you enjoy the presentation. And by the way, as far as how long this will go, might not take too long in case you all are hurrying to get to the officer meeting. But really, yeah, I'll probably be somewhere between 30 and 45 minutes. But I want to encourage people to speak up and ask questions. I know in certain groups, the idea is to not interrupt the speaker. It can be it's always a little bit difficult with these virtual talks. But I get bored if I'm just talking the whole time. And so there are a couple of instances, actually in this presentation, I think I only have one or two marked out, where I'll be asking for some participation so hopefully you stay on your toes and don't fall asleep. So the topic of this presentation about whether the Milky Way will end in a bang or a whimper, I actually switched it around from the title I gave Charlie because I wanted to make this tie into one of my favorite poems by Robert Frost, titled Fire and Ice. And so for the first part of audience participation, I have someone volunteer to please read in case anyone has a little bit of trouble seeing the words on the slide.
Sure, I'll go for it.
Okay.
Fire and Ice by Robert Frost. Some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if I had to perish twice, I think I know enough of fate to say that for destruction, ice is also great and would suffice.
All right. Yeah. Thank you, Charlie. So this is talking about the world ending, but it's interesting that a few hundred years ago, the world was considered to be like the Milky Way was considered to be the entire universe before we knew that there were external galaxies. And so if we take the world to mean that, we can think about the world ending in fire, meaning our Milky Way ending in fire. And so this is a visualization of our Milky Way galaxy. And we're evolving this forward in time in a computer simulation by billions of years. And so now we're zooming out, and we see the Andromeda galaxy and Triangulum, which some of you might know. The Milky Way and Andromeda are on a collision course. It's not very well constrained exactly when they'll hit. Some say 3 billion years, some say more like 5 or 6 billion years. And eventually Triangulum will join in the fun as well. And so you notice that there's all this material spinning around. Those are all stars. And the color is changing as well to red. And that's indicating that there are more and more old passive stars. And it's a little bit harder to say here, but this sort of collision between the Milky Way and Andromeda should be this very explosive event, producing a lot of star formation, a lot of supernova going off, which I'll talk about a little bit later. So that's one case where we have the world, our Milky Way, end in fire. Now, how about in ice? So this is looking at another representation. This is an artist's impression of the Milky Way colliding with the Virgo galaxy. And it's a little bit less visually stunning. Really, the Milky Way will not sort of obviously merge with a single galaxy. By Virgo, I mean the cluster of galaxies. And so what happens is the star-forming fuel, the molecular gas from the Milky Way, ends up sort of spaghettified and gets stripped away from the Milky Way. And then we end up running out of stars. So that would be the world ending in ice, or the Milky Way ending in a whimper, as I would say. And so this is a little look at what the Virgo cluster might look like if we were to be able to look at it in much higher detail. This is a simulation showing the dark matter distribution. And so each one of those globs represents a galaxy, and in the center you'd have M87 with its supermassive black hole. Let's taking a look at Virgo. And then this is a slide showing a range of different galaxies. So on the far right, we have something like Virgo, and we see that this, the y-axis, the baryon fraction, so this is the amount of stellar material, like in this movie. You're seeing the stellar disk and to some extent the gaseous material compared to the dark matter distribution, which is really what dominates the mass. So the fraction is always much less than 50%. This dotted line is showing 17%. And this dotted line corresponds to WMAP or Planck observing the cosmic ray microwave background. So we have a pretty good idea of what this is from WMAP and Planck to satellites. And we see that clusters have all their baryons, whereas the Milky Way, this star, is missing about 10 times the amount of gas in stars that one would expect it to have. And in terms of observations, we see that there are all these galaxies that we observe. However, you need some pretty fancy filters to see what's going on, to see all this gas that's being ejected, and possibly also preventing new material from falling onto the galaxy. So on the far left, we have M82, which you all might know as the cigar galaxy, since there are a couple of other cases here. NGC 3079 is also a dwarf galaxy, and NGC 1569, this sort of tentacle-like structure is showing radio emission. So I don't think that this was Arecibo, no, it was Kip Peak, and it's showing the neutral hydrogen. So there are a couple other images of galaxies here that I'm showing from the Changes survey, and these are again showing just the optical. But if we add in some radio emission, like we were looking at before, notice that there's very extended radio emission, much farther than you have simply material in the optical disk. And this radio emission is coming from a combination of magnetic fields and cosmic rays. So Charlie mentioned that oftentimes we have discrepancies. So this was the discrepancy. Why does the Milky Way have so few gas and stars compared to what we expect? Typically, this is because we're neglecting some physics. So this is a slide looking at the water cycle on Earth, because it's actually kind of similar to what's going on over here with this gaseous cycle. So we have some evaporation, condensation, precipitation, and this goes on, as everyone knows. A little bit more, I guess, in precipitation in the form of snow than rain in Michigan in the next month or two. Although I guess there was some rain, I think about a week ago. And then in the circumgalactic medium, so this is the region around the galaxy, we have something similar going on. You have outflows, those winds that I was showing before. Some of that material escapes, as I was saying. Some of it might actually not have a high enough velocity. It recondenses, it accretes onto the disk, and you have more star formation, more supernova. And so you might have a similar cycle going on. So back to the cosmic rays. Back in 1912, Victor Hess, who's pictured here in right before one of his hot air balloon expeditions, discovered that as he went up in the Earth's atmosphere, there were more and more accounts of this high energy radiation that no one had observed before. It's higher energy than gamma rays, and since it seemed to come from the cosmos as opposed to Earth, it was called cosmic rays. Now, in the ensuing decades, they realized, I think even slightly before Victor Hess won his Nobel Prize, that cosmic rays actually gyrate along magnetic field lines. They get deflected by Earth's geomagnetic pole, and therefore they're charged particles. And so this is showing what cosmic rays are as a function of energy. So we have mostly protons forming cosmic rays, but then there are also considerations of helium and iron nuclei here, as well as electrons, positrons, even antiprotons, which you don't tend to hear about too much. They don't last for a very long time, but cosmic rays are produced in such energetic events that, sort of like the Large Hadron Collider, you do produce some small amounts of antimatter. And so this is looking at a whole slew of different experiments on Earth. This Tibet AS Gamma is in Tibet, and AMS is one of the missions that was on the International Space Station. They have a sequel mission going on right now, which is called AMS-2. And so there's a whole lot of different cosmic rays. Now this is showing energies all the way up to 10 to the 11 GeV cosmic rays. So this is roughly 1 million times higher energy than even something we've been able to produce at the Large Hadron Collider. Large Hadron Collider, we get maybe up to 10 to the 6 GeV. And so in terms of thinking about what does a GeV mean, it's a unit of energy. If you were to take all the momentum from 1 GeV cosmic ray proton and say that your body absorbed all of that momentum instantaneously, you'd feel the same impact as a 100-mile-per-hour tennis serve from Serena Williams. So, or imagine getting hit, I guess a little bit less, but getting hit by a 90-mile-per-hour baseball. So it's a lot of impact from a single particle. Now, these cosmic rays, we're primarily interested in them in terms of understanding how they might explain these observations. So we have this extended radio mission. We observe these winds. The big picture question is, how do you eject this material? We think it's supernova, releasing energy, but we don't know whether it's the thermal energy, sort of like a bomb going off, or whether it's the cosmic rays that are accelerated by the supernova. And so the way that cosmic rays might drive a wind is they exert a pressure gradient force on the gas. And so this is the same reason for if you have a door that mysteriously slams shut, or you close it and then it just kind of squeaks open. That's due to typically some sort of pressure gradient occurring between your room or your house and the outside. And so in terms of looking at the galaxy, we have high density medium near the middle of the galaxy where we have a disk. And then as you go farther away from the galaxy in the direction away from the disk, you end up with less and less material. And so if cosmic rays are able to diffuse out of the galaxy, then they eventually encounter some low density material, which is easy to accelerate. So it's sort of like if you were to detonate a bomb in the air, or think about an atom bomb being detonated in the air, it produces this huge mushroom cloud. But if it's detonated underwater, if it's in high density, then you don't really see all that much. And so this is looking at different advection and different fluid transport processes. So cosmic rays, although they're particles, they can be described as a fluid since their size of scattering is much smaller than the size of the system. So cosmic rays tend to scatter off of magnetic fields on the scale of the solar system, whereas we're caring about the galaxy as a whole. So this is showing some mousse that are being advected along with the river. So advection means that whatever your object is, it's simply carried along with the fluid's motion. We have a case for diffusion. So this is really some advection plus diffusion. We have a hydrothermal vent here, which is venting some plume, and that plume is buoyantly rising, but as it's rising, it's diffusing outward. Okay, and then the new thing that I added to sort of this work is looking at temperature-dependent diffusion. And so for cosmic rays, that's sort of like this animation where you have faster transport in a cold medium and slower transport in a warm medium. So as cosmic rays travel from very cold pockets of gas to warmer pockets of gas, they're braked. And so my advisor has looked into this in quite some detail. So this is looking at two different galaxies, one where there is no cosmic ray transport. And so there's a very sharp disk, which you can see in the brighter colors, and then very tenuous, low density gas surrounding it. Whereas if you include cosmic ray transport, there's suddenly all this material that was in the disk that gets ejected in a wind, similar to the observations that I was showing earlier. And for my work, I did something similar, except instead of looking at a full galactic disk like my advisor, I did a zoom-in simulation. So he was looking at a scale of 100 kiloparsecs on a side. So it's a little bit more than 300,000 light years across. Well, I guess this is 200 kpc across, so more like 500,000 light years across. Whereas I'm looking at just about 10,000 light years across. So it's much smaller volume that we're looking at to do higher resolution simulations. And so on the far left is the case if cosmic rays are simulated to only advect with the gas. You have this disk, which is a bit larger in its vertical extent, but not a lot of wind, pretty low density material, farther away from the central disk midplane. If you include diffusion, then similar to my advisor's work, you see that there's some higher density material which gets blown away from the disk. And then if you include this temperature-dependent diffusion, what this ends up doing is, because the temperature is coldest near the middle, which is where star formation happens, star formation then ends in a supernova explosion. So they blow out these low-density cavities, which are very hot, and those buoyantly rise in this medium. So you have essentially a high-density cold phase and a low-density warm phase surrounding it. In this case, there was a much more vigorous supernova going off, which is why you see these bubbles, whereas you can maybe squint and see them in this case, but the contrast is not as obvious. And so in this case, I'm showing a number of different results. So in the top row, we're looking at the wind velocity. In the middle column, we're looking at the cosmic ray number density. And in the bottom row, we're looking at the magnetic field strength. And so this is looking at the advection run on the left, the ordinary diffusion run in the middle, and the temperature-dependent diffusion run on the right, where colors are looking at different times. So blue colors are early times, red colors are later times. And so what we find is that the wind velocity, even at late times, is several hundred kilometers per second in the temperature-dependent diffusion case, and much lower or even inverted, showing some signs of inflow for the advection case. And this high cosmic ray number density and magnetic field strength, so you go away from the midplane, suggests that there might be enhanced radio emission, like I was showing several slides ago. And so another thing to look at, especially in terms of thinking about looking at the evolution of a galaxy, is its star formation rate. So basically, we're trying to understand what happens to the baryons, but also understand what happens to the stars. Do you end up with more stars or an end of star formation? And whether you end up with kind of a bang of star formation, like in the merger of galaxies, or do you end up with just a gradual decay of star formation? And so what we find is that the cosmic ray transport really impacts what happens. In all three cases, there is a burst of star formation, but it's a much stronger burst of star formation in what we consider to be the most physically realistic case, with that temperature-dependent diffusion, and then a much weaker burst in the advection-only case. In all three cases, the star formation gets to pretty low values at end times, at the end time of the simulation. This is only looking at a few 100 million years into the future. But this is in a pretty idealized setup. This is a little bit more at understanding what the important physics is than understanding what's happening to this galaxy in billions of years. And so this is looking at temperature-dependent diffusion, which has to do with this process called ion-neutral damping, which occurs in molecular clouds. Another student in the group, Paco Hogan, looked at the effect of turbulent damping. So he considered, turbulent damping occurs at this interface between the disk and the halo, where you have all this material which is stirring around as supernova go off and launch this material around. And that also impacts cosmic ray transport. And he found pretty similarly that you also have very different properties of the medium if you include damping versus if you neglect it. And this is looking at the gas density on the left, similar to what I was showing, with a different color scheme, and then looking at the cosmic ray number density. We have pretty high cosmic ray number density in the disk, and then it drops off, similar to what happens with the gas. And so that's the main part for my cosmic ray winds project. And so the key point is that transport is really important, and this is really basically trying to understand what happens to these galactic winds, particularly whether this really turns off star formation, which we seem to have. So although you have a bit of a bang when the Milky Way will collide with Andromeda, nevertheless things cool down pretty quickly, versus we were wondering if you potentially just lose all this gas in a wind so quickly that you don't have very much of a burst in star formation. And so then looking at a galaxy falling into, like the Milky Way falling into the Virgo cluster, it's really talking about this ram pressure stripping process. So this is ideas if you have a dog sticking its head out the window. So let me ask for some audience participation. I guess I'll go back to presentation. But for some audience participation, I'll need someone to chime in. What happens if a dog sticks its head out the window as you're moving along maybe 20, 30 miles per hour down a road?
Likes to bark.
Likes to bark. What about, does it like to stick its tongue out?
Yeah.
Yeah. I've seen
Yep.
that. Yep.
Side, with the hair.
Yeah. So the hair and maybe the tongue as well gets kind of blown back.
Mm-hmm.
And so that's
Happy.
wind pressure in action. So it's sort of like a wind force, if you will. And so as a galaxy encounters a galaxy cluster, you can't really see it unless you're looking with an X-ray telescope. There's a very diffuse, high temperature medium that's surrounding the galaxies in a galaxy cluster. And as a galaxy like this NGC 4402, when it collides with the cluster, what happens is that the material from the galaxy ends up being blown out. It gets basically evaporated into the cluster. And so this is showing one particular case. And so this is really important because there are a lot of things about what happens to a galaxy when it falls into a cluster that we don't really understand. So for one thing, what happens if we have some molecular clouds, which would be forming stars, what happens to those guys? If you have, do you end up again with sort of a bang where you trigger star formation, or do you just remove all the material like in that artist impression where you just kind of have a whimper of decreasing star formation? You have something going on with the magnetic fields and cosmic rays. That's the primary thing that I'm interested in. And does this happen more in the outskirts or even in the center of the galaxy cluster? And so this is really important in terms of this observational trend. It's called the far infrared radio correlation. And so this is observed for galaxies in the field as opposed to in clusters, where we have surface density on the x-axis and then this ratio of far infrared to 1.4 gigahertz radiation on the y-axis. And so there's a very tight trend, especially at higher gas surface densities, that looks a little bit differently when you're looking in clusters. And so what is driving this correlation? Both the far infrared as well as the radio is coming from massive stars. So if you have O and B stars, these are the biggest, baddest, brightest, hottest stars. They produce a lot of UV. They have very dusty surroundings, which absorb the UV and re-radiate, that is far infrared. And then these O and B stars are the ones that go supernova. They produce cosmic rays, and those cosmic ray electrons produce the radio emission. And so that's all very interesting, I guess, from my perspective, from a theoretical point of view. But when some people decided to take a look observationally at what the far infrared radio correlation looks like for cluster galaxies, what they did is they observed with the very large array, so this is a radio telescope, and they found that there were deficits in regions for ram pressure stripping galaxies, but overall global enhancement, which is a bit counterintuitive. And so on the left, we have the far infrared emission that was observed in different contours. And then on the second to left panel, we're looking at radio emission. And so what they did in this third row or third column is they took the far infrared emission, they produced a model radio emission from the correlation, and then divided that from the observations. And so in yellow, you see regions of enhanced radio emission, and in black, regions of deficit. And so for the top as well as the bottom galaxy observed, there are very strong regions of deficit that are kind of surprisingly along the region where the galaxy is approaching the cluster. And that's surprising because when we look at a galaxy falling in, it almost looks to me like it's a little bit brighter on the leading edge, whereas it has material being removed on the sort of backside of the galaxy. So the expectation theoretically was that it'd be brighter on the leading edge and it would be dimmer towards the trailing side. And instead, observations seem to find the exact opposite of that, where you have a deficit of radio emission on the leading side and enhancement on the trailing side. And so in terms of understanding what's going on here, it'd be really useful to include cosmic rays in simulations, since existing simulations neglected cosmic rays. And so this is just showing a couple more galaxies. And so one idea is that what's going on is that you have material being removed from the leading edge, and although you have the existing stars there, there's not a lot of cosmic rays to shine in the radio. So you have some preferential stripping on the leading edge, and then you have shocks being driven through the interstellar medium that accelerate cosmic rays and increase the radio emission on the trailing side. And so this is a simulation without cosmic rays, again from my advisor's work, where he considered how different things look if you include magnetic fields on the left versus without them on the right. So I'm going to ask for some help again. I'm looking for three noticeable differences between the galaxy or the picture on the left and the picture on the right.
Picture on the right seems more fragmented for some reason than the one on the left.
Mm-hmm. Yeah, lots of more cores versus kind of more filamentary structure. Okay, great. That's one thing.
Wider horizontally.
Diffusion that's leading to the disbursement laterally in the image on the right.
Yeah, so I think there are two voices that are kind of saying the same thing. It's wider on the right and narrower on the left. And that has to do with magnetic fields acting almost like rubber bands. They provide some tension, which holds the material together, which is absent on the case on the right. And then one more thing. What's going on?
The flow on the left looks like it's almost completely detached from the galaxy, as opposed to the one on the right. It looks like it's completely detached from the galaxy, as opposed to the one on the left.
Yeah. So this one on the right, and you can notice that, it's very detached, very core-like. You can maybe even notice that there's more of a core-like element to the galaxy. So both of them have these little holes, but from my eye, there's even more holes and some cores on the leading edge in the hydro case, whereas in the case including magnetic fields, there's really not a lot of material on the leading edge, and instead you can kind of connect the dots as you go down the tail. All right, great. And so moving on from that, this is some details for the simulations that I'm about to show on the next slide. And so the main points are that we have about 1 trillion times the mass of the sun in dark matter. That's similar to the Milky Way. We have about 100 billion stars, and that's again meant to be similar to the Milky Way. And then about 10 times fewer mass in gas, then that would be like hydrogen, predominantly hydrogen, and a little bit of helium and heavier elements. We have a magnetic field strength, which is microgauss. So this is very weak compared to terrestrial standards. The Earth's magnetic field is roughly 1 Gauss, and household magnets tend to be tens to hundreds of Gauss, which is why for the SI system of units, magnetic fields are dealt with in Tesla. It's a bit of a larger unit than the Gauss. And then the physics that I'm including is radiative cooling, self-gravity of the gas, and star formation and feedback. So there's quite a few more bells and whistles that I'm adding in addition to the cosmic rays for my simulations compared to my advisor's work. And so here I'm showing 3 different galaxies at 200 million years into the evolution. And these black dots are showing the magnetic field to try to understand what's going on there. And so there's a lot of mess, in this case on the left, where there are not any cosmic rays. In fact, there's again some holes in the disk, which we saw back here in the hydro and even a little bit in the MHD case. So you have some holes in the disk due to very vigorous supernova going off. You have a much smoother disk in the case with cosmic rays advecting, and then something more intermediate when cosmic rays diffuse. So when cosmic rays are only allowed to advect, they stay in the disk pretty effectively, whereas when they diffuse, they also drive a little bit of a wind. Really, the ram pressure, this wind force, is doing most of the work. So you don't notice much of a wind, but what happens is the cosmic rays leak out of the galaxy a little bit, and so they don't provide quite as much sort of support to holding the galaxy together as in the advection case. And then there are a couple different things that I looked at for this work, which is still going on right now. So this is looking at the star formation, and it's kind of interesting. We were expecting the star formation to be pretty low throughout. There are some people that have argued that you might have an enhancement of star formation as the galaxy runs into the cluster. You have a shock that can increase the star formation rate. And we did find something similar to that in the no cosmic ray case, where there's this very high spike in star formation. Whereas when we include cosmic rays, there is still a gradual increase as this galaxy is plunging into the cluster, but then it starts to die off. And we're interested in running this for a longer time to see what the asymptotic evolution looks like. But so this is suggesting that a rather different picture than the artist's impression before. When the Milky Way eventually runs into the Virgo cluster, which won't happen for another 70 billion years, it will really be the Milky Way plus Andromeda galaxy colliding then. We might expect there to be a bit of an increase in the star formation before the Milky Way Andromeda galaxy eventually loses all of its star-forming fuel. This is looking at the amount of material that's being fed to the galactic center. So I mentioned that in this case, we have a sort of blow-up of the disk close to the galactic center, whereas, so fun fact, if you're looking at the solar system, The solar system is about 2/3 out from the galactic disk, so we'd actually potentially get stripped away, which wouldn't be a problem per se to our solar system, which, well, in 70 billion years, we'll hopefully have moved on from our solar system. But at that point in time, whatever remains would probably be leaving the Milky Way entirely and ending up free floating in the Virgo cluster somewhere. And so this is looking at material flowing into the galactic center. There's a very strong gas flow, roughly 40 kilometers per second for the no cosmic ray case, and much weaker gas flows when you include cosmic rays. This is looking at the amount of material in the disk, so looking at how that gas in the disk, which is the fuel for star formation, ends up getting pulled away. And we notice that there's not a very big difference between our different transport cases so far. I'm hoping that there's a bit more of a difference at later times. It'd be a little bit more interesting, but if there is no big difference, then that's fine, if that's the way it is. But overall, there is a loss of roughly 50% of the material that could form stars over just 200 million years. So although it will take roughly 70 billion years for Milky Way to run into Virgo, once it does so, it won't take very much longer for it to start losing all of its gas. And then this is looking at the amount of material that, although it might leave the galaxy, eventually gets kind of pulled back after some duration of time. And so this is going to kind of prolong the fate of gas being removed from the galaxy. So there's roughly 1 billion solar masses that falls back over the course of the simulation. But remember, we started with 10 billion solar masses, so there's not really that huge of an effect. It just increases the duration by maybe 20-30%. And then this is looking at the radio emission, one of the sort of motivations for this project. And overall, we find that whether looking with advection transport or diffusion transport, there's a very strong enhancement relative to a case without any ram pressure stripping in these dashed lines. So we do notice enhancement of the global radio emission, and something that I'm interested in looking at next is whether we reproduce those regions of radio deficit or not. And so in summary, for this project, we also find that cosmic ray transport really does a big deal both in influencing the disk morphology, whether you have a blowout of the nuclear structure or a shielding of the disk or something in between, as well as the amount of accretion onto the galactic center and how that impacts the star formation rate. We saw that the radio emission gets boosted with ram pressure stripping, and we're going to be looking more into that in the future. And okay, I probably talked a little bit too quickly there, because that is the end of the presentation. I'm very happy to take questions if you all have any. I think I can jump back into my PowerPoint, but I'll stop screen sharing so I can see if there are any questions. I think I'll turn my light on too, because it's gone quite dark here now.
I'll tell you what, as long as it stays under control, it has pretty much. Anybody wants to ask a question, go ahead and unmute and fire away.
Does the form of the cosmic radiation play any part, or is it just the energy that makes a difference?
No, that's a good question. So the radio emission is coming from mostly the cosmic ray electrons, whereas most of what I was talking about, I never really, defined it, but the cosmic ray protons are really what have the bigger impact as far as pushing gas around in galaxies. They're the dominant energy source. Their pressure gradient is what drives those winds, as well as suppresses star formation and does all this sort of fancy stuff. But the radio emission is also very important, and so that's a key distinction. Now, as far as the antiprotons and like positrons, those are in very low quantities where we don't really expect them to matter. And it's interesting that you mentioned that, though, because I was going to say we don't really expect helium and iron nuclei to matter. However, they at a certain energy range, I think it's 100 GeV, helium will start to dominate over cosmic ray protons, and that will impact the acceleration as well as the energy losses of the particles, which no one has really looked at yet. So maybe someone in my advisors group, or maybe that's something I'll look at in the future. But so far, everyone just assumes when you talk about cosmic rays, you're talking about cosmic ray protons, except for the radio emission coming from the electrons.
What is the coupling mechanism between the cosmic rays and the gas here? Is this just collisional, or is it magnetic fields, or how does the momentum get transferred from the cosmic rays to the gas and vice versa?
Yeah, good question. So the way that they're coupled is through the magnetic field. So cosmic rays, as being protons or electrons, they gyrate along magnetic field lines. And if there's a perturbation in that magnetic field line, then it's almost like they hit a brick wall and they'll reverse direction. So there's cosmic ray collisions with magnetic field structures, which so cosmic rays exchange momentum with the magnetic field, and then the magnetic field will also accelerate the low energy, just protons or hydrogen nuclei, helium nuclei, the other gas that's in the galaxy. And so it's really through the magnetic field that the cosmic rays and the gas are coupled.
So is there a contribution from the neutral gas as well, or is that just basically driven by collision with the ionized gas? There is an important influence of the neutral gas in terms of that temperature-dependent diffusion, where those neutrals, essentially because they don't feel the magnetic field, when they have some collisions with the ionized gas, they're able to basically damp away magnetic irregularities. And as a result of that, cosmic rays are able to be transported much faster. So basically, the cosmic rays, don't communicate any force to the neutral gas, and therefore they tend to travel straight through cold neutral gas at the speed of light, whereas in hotter regions they scatter off of those magnetic irregularities more. I'm not sure if I quite answered your question. Maybe you could ask it again or rephrase if I glossed over a point. I'm a chemist and not an astrophysicist, so
Okay.
I keep thinking ideal gas law.
We do tend to model these things as ideal gases, but the iron neutral friction is really more of a plasma physics effect. So at that point, it's a little bit harder to think of them as ideal gases.
Yep. Thanks.
Yep.
Any other questions for Ryan?
Well, I guess I just have a question. I'm wondering, is your work with cosmic rays, is that and trying to figure out how that influences the development of a galaxy, is that a new approach, something that hasn't been considered? You said we didn't consider the physics before, so are you I'm thinking about the energy of the optical energy that comes out of a galaxy and the radio waves that come out of a galaxy. And now you're talking about cosmic rays, has that been considered before, or is this the new part of your work?
Yeah, good question. So my advisor had considered the influence of cosmic rays in terms of driving galactic winds. However, no one had considered cosmic rays yet in terms of ramp pressure stripping. So in terms of the galaxy falling into, like Milky Way falling into the Virgo cluster, no one had considered cosmic rays in that process before. So I'm the first one to do that. And then in terms of the Milky Way, although my advisor had considered cosmic rays, he hadn't considered the temperature-dependent transport. So that was the new contribution that I gave for that work.
More questions? No more? Okay, last call. More questions for Ryan? Okay. Thank you very much, Ryan. We appreciate it.
Yeah. Thank you, Charlie. And thank you all for coming by.
Very welcome. We usually provide our guest speakers a club t-shirt or a club cap as a small token of our appreciation. But on the other hand, Ryan is actually not a guest speaker since he's a club member, so that technically disqualifies him. However, I would suggest that we not let little technicalities like that get in our way and offer Ryan a t-shirt or cap. They're baseball type caps anyway. Do you have a preference, Ryan?
I'm a baseball hat collector, so I'd go for a cap.
Cool. They are nice looking too. We have two types. One is more of a standard higher profile, like most baseball caps. And that one has an elastic band in the back. And I believe Doug Scoble can correct me if I'm wrong, that comes in I believe it's a small, medium, and then a large size. The other version is a less shaped one. It's a little more floppy on the top, lower profile, and it has an adjustable headband. Actually, I have both. I kind of like the floppier one a little better myself, but I believe we have both.
I tend to like the adjustable bands a bit better.
Cool. You got that, Doug?
I got that, and
cool.
Ryan, I have your address too in the database, so if it hasn't changed in a while, I'll just send it to that address.
If it's in Michigan, it's going to have to wait, I think, 3 weeks since the package room is closed right now.
Okay. Well, whatever you prefer, you can send me an email. I can send it to you wherever you are now, or however you want to do it.
Okay. Yeah, I'll get an email contact with you then. Thanks.
Actually, I'm thinking, Doug, I'll just drive it out to him.
You're welcome.
Go right ahead.
It might blow my lease mileage, though.
You think?
I mean, you'll put Adrian to shame driving just 2.5 hours to take a picture over the water.
That's true. That would trump him, wouldn't it? So.
Yeah.
Oh no, we'll find a way to beat that. And matter of fact,
I was gonna say, the next thing I know, you'll be heading for Alaska or something.
Yeah, we'll beat that. But I actually have. I wanted to share with you, Ryan. You're out there in San Francisco. I'll share an image that I took while I was there. And since it's lowbrow, it's a nighttime image. So there you go. San Francisco, the Golden Gate Bridge at night.
Beautiful.
Appreciation for coming out. I actually have also, and I gotta find it. I tried to get stars on the Golden Gate Bridge, and Yeah, it moves a lot, but I actually did get stars on the north end, anchoring the camera on the bridge and just pointing up. So it is possible to get stars off of the bridge. I'd have to visit again one of these years before trying to see if I could get a meaningful star shot out there. In your picture in the backdrop, you've got the north tower. That's basically where I took that shot off of the north tower. So
I'm kind of surprised. So was it late enough where you didn't really have a lot of headlights?
Yeah, I don't remember. I don't think I had a moon either. Okay. I was actually I was on my way across to the other side of the bridge when they were closing it. So
okay.
Yeah, so I was escorted off by security, but not without. I didn't get a fine or anything. In fact, I got a story about the bridge while being escorted off. I got halfway back on foot and then driven the rest of the way. So that was a fun experience being out there. I'm hoping to get the view that you've got in your background. If the next time I can get out there, I'm hoping to get up on that hill and take my own shots there. But
yeah, I imagine you could get some, as long as there's not too much light pollution from the city. I imagine you could get some pretty nice images of stars along with the bridge from red headlands. Yeah, it's really pretty nice. Definitely for sunrises and sunsets.
Yeah, I guess that's a sunrise that you've got, because when I was there, the sunset was clear in the Pacific on the other side. But yeah, it was a nice. And of course, nothing to do with your wonderful talk, but you brought back memories when I saw the bridge and say you're an hour away from there. So yeah, so I appreciate that too.
Yeah, it's nice to be home. Just wish it was a little bit less stressful of a trip than usual, but hopefully things will be getting back to normal in a couple months, or at least by next year.
Yep, sounds good.
Okay, I think we're ready to move on to officer reports. I don't have anything in particular, although I did want to wish everybody that celebrates it that I hope they had a happy Hanukkah week and are enjoying the last day of Hanukkah, in fact, for 2020. And for those of us that celebrate Christmas, I hope you have a good Christmas next week. And we all celebrate New Year's, so I hope that goes well for everybody also. And with that, I will go to Joy. Is she still with us? Okay, Joy did say she might have to leave early. I'm kind of scanning the screens here.
I don't see her online, so.
Yeah, I don't see her.
Yeah,
I don't blame her either. Probably still kind of recovering.
Okay. How about you, Adrian?
I got nothing to report. Everyone knows of my adventures with photography, but as far as lowbrow business, I am clear for this month.
Thank you. I think I see Jim Forrester there.
Nothing really to report. There's been a little talk of star parties this year, and my experience with both the Texas Star Party and Okie-Tex is that part of the country thinks very differently about some important things from this part of the country. For example, just looking at the election map, Cimarron County in Oklahoma, where Okie-Tex is about as, they voted 90% for Trump. And in the past, I've had, wouldn't call them run-ins about science with the Star Party, but that's essentially what it is. And the things that the Oklahoma City Club will tolerate to be able to use that venue. And the locals supply a lot of the service to the Star Party, like meals and and other things that are important to the operation of the event. And so, you know, I just want to let people know they have to be pretty careful with you know, planning to attend these events. I'd really like to go in October. That's when Okie-Tex takes place in 2021, but I just, you know, whether people are going to be vaccinated or social distancing, and actually, you know, there's what they'll say on their website and what they'll actually do. I just want to caution people to be very careful. So
Thank you, Jim.
that's all I've got.
Thank you. How about Dave Jorgensen?
I have nothing to report. Let's see, am I unmuted this time?
You are.
Yep.
Okay, all right.
We did hear your report. We thought we were going to go on forever. How about Don Foley, our newsletter editor?
Hi. Yeah, I've been doing quite a bit of thinking here this year, and I decided I'm not going to run for newsletter editor for next year. So this will be my last year for the newsletter. So when I send out the January newsletter, I'll also put in a pitch explaining that we're looking for candidates, people who'd like to be the newsletter editor, and talk about the pros. You know, it's not that hard a job to do, and I'm sure there's lots of people who enjoy working with their computers and editing and such, and we'll find someone else who can take.
You do leave a hard act to follow, though, Don, and all your work all these years has been appreciated.
Yeah. Yep. So I just there's other things I want to do. Every month it comes up, and it's not as fun as it used to be.
And you notice it keeps coming around faster and faster.
Yeah. Yes, it does.
Especially this year.
Yeah. That it?
That's it.
Okay, thank you, Don. We'll move on to Jack.
Well, my report will be kind of short. The 8-inch F6 Starliner was returned back to the observatory. John Bennison's been using it and was done with it. We picked it up and returned it, so it's back at the observatory. And I have been out there a few other times, and everything looks fine so far. And I am working with it's electric heater for the observatory, something to try and heat up the observatory during the winter months, but it's still in exploratory stages. Other than that, that's all I have to report. So I'm going to wait till next year. We can reopen the observatory up and take it from there. That's about it.
Have there been any other discussions about the Wi-Fi?
No, the last time we had that meeting, the end of November, that first week in December, I think it was December 3rd, I think. I have not had any discussions at all with anyone. The thing to remember about this is none of this was ever considered a decision-making meeting. It was more of a informational meeting. Like last time we were out there, they took some measurements and figured out how many feet away you were from the telephone pole, how many feet away they were from the radio, the observatory was from the radio observatory and stuff like that to get an idea for running cable if they do. But there are other people that came up with some analysis that said, there were some local cities that were all cable, not Wi-Fi, and they wanted to contact them for a bid. So none of this has ever been cast in stone, as they say.
Okay.
So I've been waiting, but I have heard nothing from them on this last meeting. So I'm not going to make any statements about it until we get something a little more concrete as to a final decision. And I don't think that's going to happen till sometime, I would think, mid-2021, only because of all the other costs the University of Michigan has had to endure with this COVID-19, and this other cost of bringing Wi-Fi out there to Stinchfield Woods and that is another expense that has been budgeted through the College of Engineering and through SCAS and the university itself. So those are issues that have to be addressed, and that's way out of my pay grade, as they say.
Yeah.
It's, you know, they're going to figure that out how they want to do it, and who knows? With all this going on, somebody might come up with a unique situation or a unique way of solving this, and it could be a low-cost alternative. I just don't know. So I really would rather keep as they say, keep the door open and see what flows through it before we start making decisions. But it's a good point. I mean, we've been discussing it, but
I thought if there was an update,
well, yeah, I was kind of hoping we'd get something, but I had no contact with any of the people there.
Yeah.
Well, it's going with all of the due speed and diligence we expect out of the University of Michigan. Very diligent and very slow.
I think it has something to do with the time of year too, perhaps.
Yeah, if you followed the COVID announcements of the university at all, I think it's week to week is the way things are going with that. So I don't blame them. I'm okay.
Yeah, it's very true.
Jack, I have what township is the observatory in?
It has a Dexter mailing address.
It's Dexter Township.
48130, or also known as 10280 North Territorial Road. And originally they looked at bringing in a fiber cable. There is an outlet off North Territorial Road they talked about, so that was one alternative. There's been some alternatives about some of their new I'll use satellite transmissions, but I'm not sure how effective that is in that area. There's some problems
So if I can interrupt for a second, I'm about 3 miles from the observatory in Dexter Township.
Mm-hmm.
And I recently got satellite internet because I have nothing else. No cable, no DSL. And so I've got Viasat at 25 megabits per second. The neighbor who runs a business out of her house has HughesNet at, I believe, 25 megabits per second. It's nothing like cable, but it's much better than using your phone as a wireless hotspot at a half a megabit per second. So that kind of an option might be available out there as well. It does run it's noticeably faster than what I had before.
Well, that's true. I did a study there last year. Well, wait, let me rephrase that. It was earlier this year when we did one of our first Zoom meetings. I went out to Peach Mountain and set up wireless using my car as a receiver and that. And it was not that great. I had some problems with bandwidth and some other things too. Now, what's going on at the university is a couple of departments, they're looking at gigabyte transmissions because of research, classrooms, and other types of work they'll be doing out there. And that's part of the reason why this has become a little bit cumbersome because, as you know, there's a lot of places. My house, I have 150 megabyte download, upload thing, Comcast, but getting 1 gigabyte to a 10 gigabyte transmission through a cable is something that they were looking at because of classroom activity that they want to do out there, and some research at the radio observatory. So yeah, that's why they're looking at it different. But yeah, I agree with you. If you could get a good Wi-Fi, 25 to 50 megabytes downward, and we might be okay with that. I don't know.
Yeah, I think for our purposes, that would be plenty.
Yeah,
you can stream movies on that, so I don't see why that wouldn't work for us. It's just whether we really want to do it.
Well, it's working with the College of Engineering and the SEAS group as to what they want out there. There's a third party, as you may know. Michigan Radio has an antenna out there, which a lot of people don't realize. They are looking at some upgrades there too when you bring this cable system in. I should really call it a fiber optic system is what they're looking at. That's why the expense is there. But you need that to bring in 1 to 10 gigabyte transmission to handle all the
load.
It would be everything that they're going to do out there. So I've been kind of playing piggyback and saying, yeah, that's great, and be glad to work with you, whatever we can get off of them. And they had a couple ideas, as some of you know. We did talk last year a couple times about this, about running the main wire would go to the radio observatory, but there would be a secondary cable run through the power lines that go in back of the Peach Mountain Observatory that go up that little road trail up to the radio observatory. And you could do that. And then they did at one time come out there with a device and measure the distance from those telephone poles to the observatory to get out how many feet they would have to dig to run cable from there if they wanted it. Now, the reason they do it this way, because I know some people would say, well, you ought to just tell them to run that when they run that line, run a Wi-Fi off and run another line to us. If you go into the system as it's set up, an outlet is considered the radio observatory, another outlet is considered SCAS, the third outlet is considered Michigan Radio. All three of those organizations pay for that cable system.
Yeah, the network service.
Yeah, network service, yeah. So if the club gets their own line run off that, then we in turn fork over that $5,000 down payment and $1,500 a month to run that line. And we're not going to do that. Common sense tells us we don't have that kind of income. So we are not considered a main outlet. So we would run off from the radio observatory. So that's why they're doing all this different work out there. And then we'll take a line off there with it. Once you start getting into the cost of all this, it's kind of like it would be better if we stood on the sidelines and worked out a deal with the College of Engineering. And that's what we're probably going to end up doing. We've had a good relationship with them, and there's some things that we did with them a couple of years ago, and those are important. And we're going to, I think, the best bet was to play it by ear right now and see what happens, and then follow through with them.
Yeah. And Jim,
I think that last, right quick, Jeff, I think that last thing you've just mentioned, the question that I had about us possibly going rogue and getting getting our own satellite or something for Peach Mountain, I think you just answered that by saying working with the College of Engineering would be a lot better.
Right.
And
Yes.
Jeff, I think you're about to
Well,
jump in on
I
that
was
too.
I was only going to add that in talking with James Cutler, the professor who's behind the radio observatory refurbishment, he's got a lot of federal money that he's applied for and or has gotten, and he's also all about outreach. He's a big outreach guy, and we
Yes.
sort of fall into that category pretty nicely.
Yeah, so it
Yeah,
sounds like it's
so
a better
Chris,
deal for us to wait.
So Chris Adams, how much does a satellite cost you per month?
Right now, it's an introductory rate of $85 a month, and it's going to go up to $120.
Thank you.
Somebody just made a comment all about latency as well, and I can tell you that is pretty bad. It's on the order of 600 milliseconds or so for my connection.
Yeah, that's,
I would just want to add here parenthetically, this has nothing to do with astronomy or the club, but think of a high school or a college student who lives out in that area who is trying to engage, is trying to engage over the electronic media and the difficulties that entails. And yes, this is a rather wealthy community out in that area. Nevertheless, many people face the same problems in other areas. And again, this gets a little political, but our infrastructure for electronic technology in this country is primitive. And frankly, we would be paying, we would be paying pennies or fractions of a penny on the dollar if this were a public utility and were managed as something like, water or electricity that people must have. This is really pathetic.
There is some research, I have to say that or some paperwork I've read that, they're trying to look at ways to get, I guess, like you said, make it a public utility, cut down some of the costs, and get back into some way of maintaining a certain level of control for the general public.
Almost nowhere else in the developed, industrialized world do you find this kind of impediment to information technology.
Yeah.
that's fair.
Yeah, well, it's gotta rise up in the priority for the university, and I think in order for that to happen, those radio towers would need to be active and running, and then we would end up piggybacking on that. As it is right now, that stuff is laying dormant, and they're more worried about vandals. And it's a running area. It's a place for people to walk and run, and not so much doing science out there. I think, John, the urgency for getting it wired up goes up if some of these initiatives to get funding for the area, repairing a lot of the stuff that's out there. If that happens, we would be next with our internet. Right now, we're the only game in town, and thanks to COVID, we're not actually using it actively out there as well. So it's probably a priority thing.
Well, Chris Adams is one of the games in town too, and he's penalized by the lack of publicly available infrastructure.
Right, but that, to me, it sounds like the city would have to step up, and it's an interesting discussion on who should just step up in light of pandemics and then just having internet in general, because that's just the way the world's going to be before and after COVID-19. We all should be connected there. It's like running water, like you said, but I don't know that internet service, AT&T and Verizon and all of those carriers are the ones updating their equipment, and not, fiber or not the fiber connections, and making sure that Stinchfield Woods is connected, and Chris as well. I think it's kind of a way of the world until something can be done to change it.
Well, it's because it's all about the money and not about the people.
That you could say that for a number of things. I mean, that becomes political commentary for tons of things. So it's definitely, you're definitely telling the truth, but it's the hard part is, what do we do about it until, and I'd like to see priority given to not only that area, but the Stinchfield Woods as well. There's interest, so it's just gotta pick up somewhere. Someone's got to be willing to run with it.
There is another possibility, but probably remote possibility. That is the company that I do most of my contract work for. They have a division called Rural Reach, which supplies internet service to rural type areas. It's not satellite. We actually beam signals from tower to tower. Excuse me. And typically we find new areas where we can serve, and we get other people to kind of come on board in that area. Then we put up an antenna and shoot that signal down in that area. I know they desperately want something up on Peach Mountain. I don't know who they've been talking to, if they've made any progress at all. In fact, I might ask about that and just see. But if that was to happen someday, we could probably, just depending on which way that's aimed, get access to that antenna, and I probably could even get us a deal on it. But again, whether they will get permission to do that's the big question.
Yep.
So, with that, I suggest we move on and go to Doug Scoble.
Well, hello from Traverse City.
Traverse City, Doug.
We have 156 memberships. We have $9,119.78 in the kitty. We picked up 2 new memberships since the last meeting. People just keep sending us money, and so getting new members on board. We also received a couple $50 donations in memory of the late Bernard Freiberg over the past month too. So that's where our finances stand. Don mentioned not running for treasurer. I intend to keep doing it unless you want to. Someone else wants to volunteer for the job. I think it's working out pretty well right now. Once in-person meetings resume, I probably will not be at most meetings to accept cash or checks or whatever. So if that becomes an impediment, then maybe it's time to hand it off to someone else. But for the time being, it's working out just fine for me. And people are mailing me checks. They're coming to the right address. Jim, have you checked the post office box recently or not?
Not in the last 3 weeks or so. You've rerouted most all of the sensitive material. So once the phone bill started going north, I thought, well, maybe once a month we should do it, because there just isn't that much stuff that comes to the mailbox.
Right.
And remember, Jim, if that does become a burden at any time or anything, I have a key, so I can always run up there too.
Yeah, my main problem is just remembering to do stuff. So
remember what?
There you go.
No. What are we talking about?
So I'll get up there soon and take a look at the mailbox. But like I said, there hasn't been much there, and I suppose that occasionally someone could get a hold of that box number and be sending membership checks or something like that there. But
Doug, do you ever many people send you cash, and has anybody ever reported an issue with that?
I have not. I don't encourage cash. I don't say don't send me cash, but I haven't received any. My guess is if you put it in a security envelope or you wrapped it in a sheet of paper, cash would go through just fine. So it's probably not probably not an issue. It's generally not regarded as a good idea, but sending a check, if someone intercepts a check in the mail, well, they've got your routing number and they've got your account number. It's like, well,
Yeah,
it doesn't seem much safer than cash if someone wants to intercept mail.
that's true.
One's as bad as the other. So, yeah, cash would be fine. I could mention that. Most people, I probably get 50-50 mix of PayPal and checks, and I can deposit checks with my phone. So I don't even have to go to the bank. In fact, we don't have a TCF bank office up here. There's an ATM, but since I don't have the debit card anymore, that expired, and I had to visit an office to get that replaced, I didn't replace it, so I can't go to an ATM and use a debit card. So anyways, it's checks or cash or PayPal, and I have been bugged a couple times about maybe using or accepting Venmo, which I have not joined up with. I'm reluctant to get with too many of those different kinds of things. The more things you spread your account around with, it's probably safe, but it's just more for me to track and
I think that's
all that stuff. So I'm reluctant to add more. PayPal's established and very very safe in my
They're pretty good.
I would agree. Yeah.
And Elon Musk has made a great deal of money off of that. He's doing some good stuff.
That works. So anyways, to address the in-person meetings, we've got myself and Jeff here. The intent is to continue allowing you to be and other members to still somehow be able to attend similar to this, but maybe, I don't know if it'll just leave YouTube up and stream there, or we just continue streaming Zoom, but we patch you in somehow, like everybody's behind a camera now. But in the glorious days that we're back to in person, I don't see us stopping our live stream.
Yeah, that's not the issue. Right. The issue is people actually handing me cash or a check in person.
Yeah, I guess it's hard to hand it to you through the screen. It stops at the screen, doesn't work.
I can reach.
Yeah, but it won't. We haven't developed technology for the money to magically beam its way across yet. Except
I tried
to
to send him one by putting it in my CD-ROM slot, but that didn't work. So
yeah, if the money disappeared, though, that would be interesting. Like where'd it go? But well, I think we'll figure a way out. I mean, I'm going out on a limb to say, Doug, we'll figure a way out to get it done, and if that includes teaching PayPal, we might have to consider doing that.
Yeah.
So
that's my report.
Thank you, Doug. And that leaves us with Jeff.
Well, Adrian stole most of my thunder, but I was just going to say sometime, when we get closer to in-person meetings, that'll probably be something we'll talk about and discuss how it's going to work. But I fully have been thinking about how we do that with in-person meetings, and it's probably going to be a couple of cameras for presenter, and maybe one that we can point out into the crowd for question and answer. So make it a fully remote thing for people who are not there. We've gotten, the people who have spoken up have said positive things about the online YouTube feeds and the Zoom meetings. So I think it's something that we can continue without too much problem. Tonight we had, I think peak was 34 in Zoom and 4 online and YouTube. And past that, I've gotten by my hardware issues on the 120 millimeter refractor, and now it's just a matter of making it tall enough so it doesn't hit the tripod legs. So.
Yeah, we chatted about that, Jeff. You're going north. You definitely want to have that working before you get to those guys out there.
Well, I can do the alignment, and not because the alignment requires a full 360 degrees in both axes, and that's where it hits. But once it's pointed toward the first alignment point, then we just throw the telescope on and center it and be done with it. So I think I'll be okay.
Yeah, there's most of these
I can for $138 I can buy a pier attachment for my tripod. It'll bump it up 8 inches. So it's just another $138.
Well,
You know the routine. Come on.
yeah. Well,
Hey, Jeff, I wonder
it's
if
better
Clay
than
has any.
boats.
What's that?
It's better than boats.
Yeah. What was that, Charlie?
I wonder what Clay has for an extender, if he has anything.
He might. Frankly, Ioptron's got one that fits. It's all pre-drilled and ready to roll to expand the exact mount. And secondarily, Ani has been trying to get me into an equatorial mount for months now, if not years. And
Jeff, I was wondering if we did a GoFundMe for that $138.
do whatever you like.
Well, listen,
if that could reduce the volume of email, perhaps.
I can always go ask the WAS Treasury. I just became the treasurer for WAS, and I happen to know they have a fairly decent-sized treasury.
I know the
request.
I know the treasurers for GLAC too. So, speaking of which, actually, we submitted an article to a journal the journal article will be published sometime in July. But we submitted an abstract for approval to describe what we did for Astronomy at the Beach 2020. Being online. So they have a special issue that's going to address all these remote issues. We wrote up a quick abstract of 900 words or 900 characters or less. And if they approve it, then there's a 1,500 word paper that you can basically write up and submit. And we figure the officers can write through that and put it together as a collective, because we each did parts of it. But that's the new goings on in GLAC.
By we, Jeff is basically saying he. We all signed off on it after he read it.
That was the abstract.
He wrote a very good abstract, I thought. I would have gone in there and I wouldn't have written anything better. Like he's saying, all the rest of the officers will
It wouldn't have been 900 characters either.
No, I think I would have done one of two things: gone way over 900 characters, or just stamped a picture of it, and then I would have sent it in.
That goes really fast, by the way. 1,000 characters is nothing.
Yeah.
I congratulate Jeff on that work. That's excellent work, and it really speaks well for his OCD.
Yeah, I agree.
It was just sitting in there in my inbox forever. I had to do something with it. Why is my levels?
That's more GLAC.
My levels are back down to nothing again. I don't know what's going on with the sound.
I can hear you just fine. So.
Yeah.
Okay, that's good.
Yeah.
Actually, your sound just got slightly louder.
Yeah, because I turned it up again.
Oh, okay. Yeah, when it went down.
Right now, it's floating down once again. So I don't know what it's doing.
You've got it automatic somewhere, but that's okay because we're
winding up anyway.
Yeah, we're winding up. So,
well, with that, does anybody listening have anything else to submit? Ask.
Did anyone do anything about the clouds?
That's a pretty tough one, John.
I did. I brought them in. Come on.
Yeah, you.
Well, then make them go away.
They went away briefly the night that I went to Lake Hudson, and it cleared up, and I did some Orion shots. So that was the end of Jeff's clouds. These clouds came from somewhere else, and I had to drive all the way west to avoid those. So I don't know whose clouds these are.
Again, just parenthetically, when I was a very young child, I moved from North Dakota to Toledo, and in February, and I couldn't believe it. It was like we lived under underneath a battleship. I didn't see the sun for 40 days, and as a child, I just thought that the world had come to an end, and I was living in some kind of purgation.
You said that was Cleveland?
Well, no, from North Dakota, from by the Canadian border to Toledo. And up there by the Canadian border, I mean, if it wasn't snowing or raining, the sky was beautifully clear and blue. So, what do you want to do?
Yeah, sounds like not North Michigan, more like Southern Michigan. All of the Big Ten area basically has the same weather. Cloudy unless otherwise cloudy unless otherwise. So that's just the way it is. Even New York. Well,
we don't have tornadoes, earthquakes, hurricanes,
Sharks,
or scorpions. So.
saltwater, sharks.
Actually,
bull sharks can swim in those big lakes.
Actually, Michigan is one of the more deadly places for tornadoes, mostly because people don't believe that they happen here. And so they don't take shelter, and they get killed in outsized numbers to the number of tornadoes that actually happen.
Which actually, Jim's right. Just west of here, like Lenawee County and Jackson County, that's tornadoality in Michigan. So we kind of luck out with Dexter bearing the brunt of the tornado season. Everything goes north or south of Dexter.
Yeah, we have now progressed from astronomy to meteorology. So, Charlie, what should we do?
I say we should entertain a motion to adjourn.
Second the motion.
All right.
Everybody have a good holiday.
Yes.
Yes, absolutely.
Merry Christmas.
Take care, everybody.
Stay safe.
Meeting adjourned is 9:12 p.m. Minutes will be sent out sometime soon.
Okay, cool.
As soon as I hit save.
So long.
All right.
See ya.
See ya.
Did you want to hang on,